All right, I think without any further delay, we can get started. So, welcome everyone. Thank you for joining for this webinar on the role of CFD in developing oil and gas and offshore technologies. My name is Achyuth Rajendran. I'm a technical account manager here in Convergent Science Houston office. I'm also joined by Dr. Pedram Tesray, who's a senior research engineer and application specialist in the oil and gas field. Pedram has a PhD in mechanical engineering, specializing in turbulent flows from Texas A&M, and has over half a decade experience here with us here in Convergent Science. So again, this webinar is hosted by Convergent Science, and Convergent Science develops and supports CONVERGE, state-of-the-art CFD software that is designed for fast predictive multiphysics simulations. And before we get into the webinar, if you have any questions during the course of this webinar, please feel free to put it in the chat box and we'll get it answered at the end of the webinar. Right. So who are we? Who is Convergent Science? We were founded in 1997, first as a consultancy company in the engine space. And 2008 is when we finally developed Converge, the CFD solver, and started selling it in the IC engine space. Since the years passed, we have gone on to other markets and other locations as well. We're still headquartered in Madison, Wisconsin, but we have locations in other parts of the US, Texas being one of them here, and also in India, Europe, and we have distributors in China and Japan as well. These are some of the applications we have since grown into and established a presence in. Just to list a few: the pump and compressor market, the after treatment market, gas turbine, rockets, e-mobility, wind turbine, and of course, oil and gas. And very recently, even the hydrogen market as well. So what is it about us that separates us from other CFD codes out there that you commonly find, which maybe, many of you are familiar with? I would say the primary defining feature is that you are able to generate and automatically generate a very high quality mesh at runtime, even for cases with moving boundaries. And in addition to that, we have AMR, or adaptive mesh refinement, which dynamically adds mesh where it's most needed. So with these two features in mind, we are able to be ideal for applications that include complicated geometries, moving boundaries, and physics such as fluid structural interaction, multi-phase flows, combustion because of our background in IC engines. And also recently we have added modules like optimization and machine learning to help with product design. Again, this is typically the workflow that you would encounter in some of the traditional CFD codes out there. You would import your geometry, and before you can really focus on the physics of the problem, you would have that bottleneck of meshing, either through a mesher or even using another software for meshing. And that is what we offer to get you around in Converge. So you would simply import the geometry, and with automatic mesh generation, you can have more time really to focus on the physics of the problem. So how can this help you? Well, you can avoid long meshing times. You don't have to mesh by guessing anymore. That's what AMR is really there to help you with. With AMR, you can simply show through have mesh applied where the flow gradients are most varied. Grid convergence is another thing that can, really be, if you want to do a grid convergence study in Converge through the Cartesian grid cell method, you can simply change the base grid, as we call it, and have a new mesh generated, which makes grid convergence studies much easier. And also, we have a higher quality mesh through the orthogonal cells that we use. So that's an overview of Converge, but towards this webinar here specifically, we wanted to focus on some case studies that we encounter in the oil and gas offshore market here. So we're going to focus on a few case studies in these different areas. Firstly, multi-phase. Multi-phase flows are, something we encounter daily in the oil and gas market here. Whether it be upstream, midstream, or downstream, there's always a multi-phase application of interest. So we're going to look at some multi-phase models. You're going to hear a little bit about multi-fluid, multi-phase model, and also some of applications such as the three-phase oil separator, for example, and the fluidized bed reactor, and some of those. Another is going to be the floating offshore wind platform, some of the models we have specifically for that. And we're going to look specifically at the OC6 validation effort, a case that we simulated in this area. Now, I mentioned before, pumps and compressors is an area we've been in for the last decade, really. And we're going to look at one specific case of a pump here where fluid structure interaction and automatic generation really comes into play. Erosion modeling is what we're going to look at finally. And you're going to see some models we have to simulate erosion. We're going to look at some cases in erosion in pipe flow, drill bit modeling, and yeah, we're going to look at, we're going to have an overview of that application as well. So yeah, without further ado, let me pass it on to our application specialist in this arena here, Dr. Pedram Tesray, and yeah, I'll let him take over. Thank you.
Thank you so much, Achyuth, for the introduction. Hello, everyone. My name is Pedram Tazrei. I'm a senior research engineer at Convergent Science. In this webinar, we'll be discussing some main features that can be useful in oil and gas applications. The first part of this webinar is about the Eulerian multi-phase models that we have in CONVERGE CFD. There are many other industries interested in this type of problem. For example, technology, aerospace, automotive, and even biomedical industries are among them. The figure here shows how Eulerian and Lagrangian approaches are different. As we may know, in Eulerian approaches, we solve the flow field in discretized control volumes instead of tracking individual parcels. And two main Eulerian multi-phase models, which are available in Converge, are volume of fluid, VOF, and multi-fluid, multi-field, or MFMF models. Converge can directly transport the void fraction or transport species, momentum, and energy, and calculate the void fraction or species volume fractions. Transport equation for species can be solved by transporting species mass fraction or transporting species density. And you can choose between the two. Using adaptive mesh refinement with front capturing techniques in Converge, you can capture sharp interface between the two species or each species pair. And the interface capturing models that we have available in Converge are Plick, Ettrick, FCT, surface compression, and reflux model. In this video, a tank at zero gravitational force is moving back and forth in alternating directions. And you can see that how the liquid in green starts from a resting position and reacts to the motion. And later on, you see the formation of bubble. The VOF model in Converge is used for this simulation, and we compare the results, the experiment that was performed in the International Space Station. And as we can see, Converge is able to accurately represent the liquid motion and bubble formation. And here you can see the AMR, how it refines the mesh automatically at the free surface. So today, in general, we'll go over multiple examples of AMR application, and we'll show how we can save time using that feature. Multi-fluid, multi-field, or MFMF model allows for modeling of multiple immiscible species. All right, so dispersed phases can be solid, liquid droplets, or bubble gases. In MFMF modeling, continuity and momentum and energy equations are solved for each species individually. And generally, VOF is the preferred choice for free surface flows like sloshing in a tank, free surface in a wave, filling and emptying of a tank, because we are only interested in the location and motion of the interface between the two species or two phases. But when it comes to including dispersed phase in our analysis, such as sediment transport, MFMF is more useful. Using MFMF, dispersed phase is transported along with the continuous phase using particle stress models that we have in our code. It's clear that discrete element model can be really expensive for those engineering analysis. Although it can be more accurate. In MFMF modeling, we need to account for the mass transfer between species in the system, and we couple phases through pressure field, which is shared between all species. And the coupling also can be done in through source terms in momentum and energy equations. Momentum can also be transferred by mass transfer and lift, drag, and added mass loads at the interface. We solve momentum equation for each species individually, right? We have already mentioned that. So we can expect having different cell center velocities for each species. In terms of the turbulence modeling, mixture turbulence models are applied to the mixture. And same as VOF models, we can apply front capturing techniques together with AMR in order to capture sharp interface between phases. So the first example that we're going to talk about is fluidized bed, which is an example of continuous dispersed phase interaction. Here we show a schematic of 2D bubbling fluidized bed. As you can see, lower part of the domain is filled with groupy particles with volume fraction of 54%. Uniform flow of carbon dioxide, which is fed from the bottom of the domain. You can see how it suspends the bed. And we account for particle collisions using particle stress models and volume fraction contours for both particle stress models that we have used. I mean, the kinetic theory and granular rheology show similar behavior in terms of capturing the bed expansion. And based on these contours, we can confirm that both models capture how gas flow impedes bed overpacking. The next test case is slug flow in an infinite horizontal pipe. And case properties are listed here. And we can see how flow is driven by constant velocity source term in the streamwise momentum equation. The species mass fractions are specified in the initial field. And we use MFMF model to simulate the multi-phase interactions in the pipe. On the right, we show the MFMF user interface in our software. We include the drag between the species by Schiller-Newman model. We have the option to customize the particle diameter for each species pair, or apply a global quantity for all the pairs in order to calculate the drag coefficient. We can also include other interspecies forces such as lift and also added mass or mutual mass. Because generally, if we want to simulate the particle, which is accelerated by different forces in the momentum equation, we need to account for the virtual mass effect. Also, to capture the sharp interface, we use surface compression technique, which is a pure numerical technique. Here we show contour of mass fraction for oil and water and air for two types of initialization. Homogeneous on the top and slug on the bottom. Evolution of continuous stratification, which is driven by interface forces and growth of hydrodynamic instabilities are captured. And if we compare the final response here, both converge to the same result. And this shows the effectiveness of the MFMF model for the phase interaction. Next, we study air, oil, water separator. The figure on the right shows a 3D schematic of the domain. This is a 3D three-phase simulation where we use MFMF multi-phase model. We prescribe inlet mass flow rates and outlet pressures for individual species. In terms of the CFD solver, we use simple for the pressure velocity coupling. Mixture turbulence model is based on standard K epsilon model. And the collocated mesh with base grid size of 80 millimeter is used. The species and velocity-based AMR also are used for the adaptive refinement. And here we show contours of oil, water, and air mass fractions. This type of simulation can help investigating the efficiency of separators. We can see that the difference in separation rate for each species pair is captured by MFMF modeling Converge. And the contours show that because of the density gradients, water, which is dense fluid, remains at the bottom. We have oil, which sits on top. It reaches the oil bucket and finally leaves the tank. So if I forward the video, we can see how eventually oil leaves the tank. AMR with surface compression, we can see that it did a great job with sharp interface between phases. And this is a fine kind of resolution case with total cell count of 7 million, and it costs around 27,000 core hours for 180 seconds physical time. The second part of today's webinar is about floating offshore wind platform. Floating offshore wind turbine designs are generally challenging because there are a lot of physics involved. Wind and wave loads, cable dynamics, and structural responses to loads. Also, disparity of lengths and time scales, as we have shown on the bottom right, adds to the complexity of flow resolved simulations. Simplified engineering models may not be sufficient to model all those phenomena yet, but we need to use higher fidelity approaches then. At Convergent Science, we have been investigating a coupled simulation strategy to simulate these type of flows efficiently. And on the top right, we show a semi-submersible floating offshore wind turbine that is suspended in water and held in place by mooring cables. The first thing that I want to focus on is cut cell approach and autonomous meshing. That is a huge advantage for complex moving boundaries, and we are able to easily handle mesh generation and mesh motion in Converge. In order to save some computational cost, the blades can be modeled using suitable rotor models. It can be actuator line model and refined actuator disk model. The mooring lines are also modeled using lumped element structural model. We also have the capability to couple the structure and fluid domain solver for low density ratio cases. It is done through implicit FSI coupling. We have also the ability to generate various types of waves and impose realistic turbulence in both inflow and also as the initial field. And also for the wave simulations, we can use VOF models coupled with front capturing techniques to resolve the interface. Reasonable AMR setting can also increase the computational efficiency for these type of simulations. We have already talked about or presented the results for OC4 in the past, and here we will present OC6. OC6 stands for the Offshore Code Comparison Collaboration Continued with Correlation and Uncertainty. It is an international research project on validating the tools for the design of offshore wind systems. It is run under International Energy Agency organization. And specifically phase 4 of OC6 addresses viscous hydrodynamic loads for floating offshore platform structures. On the right, we show a full scale next to scale model of 3.6 megawatt Siemens turbine and its tetra spar platform. And in the support structure in the middle, hull and keel move together as a solid entity, and there is no relative motion between them. Okay, and dimension of the support parts are also listed in the table. The mooring system contains 3 mooring lines at 2 levels, lower section and upper section. There are additional anchors in the smaller test system compared to the full-scale offshore platform. The first one is 2 yaw bridle lines that are used only for certain extreme conditions that are not studied here. And that's why we haven't included that in our CFD simulations. And one umbilical line, which is for data transferring from the platform to the acquisition system. This part is actually included in the CFD simulation. Here, we have the details of the case setup in terms of the solver type, numerical scheme, grid strategy. We can clearly see how AMR creates finer mesh at the interface, air-water interface. We, in this section of this webinar, we will present results for 2 types of loading, free decay and induced motion by irregular waves. All right, for the OC6, we already know the equilibrium state. All right, so to simulate the free decay, the only thing we can do is to displace the whole platform from its equilibrium state and see how it reacts to that displacement. And here we are showing the amount of displacement in all 3 heave, surge, and pitch directions. This animation on the right shows the heave decay. So we validate the displacement of hull center of gravity against the test data for 3 modes of motion. The wiggles that we can see in the surge plot is generally related to the motion of the hull center of gravity. The experimental data generally also show stronger damping in surge and pitch, which can be related to some uncertainty with the umbilical line properties. Those properties are released by NREL So there might be some uncertainty with those properties. The other uncertainty is about the friction between the mooring cable and bottom of the tank, which is not again included in our computations. But in general, the level of agreement is reasonable. We have three animations at the bottom here, which show the 6 degree of freedom motion. For this simulation, this type of simulations, we have around 0.6 million cells, and the total cost is around 800 core hours for 600 seconds physical time. And the next loading type is the regular wave. We instead of displacing the platform from its equilibrium state, here we apply irregular waves at the inlet. And then we measure the movement of the floater. So we have a time series data, then we can do FFT to convert them from time data to a time domain to frequency domain. This way we can analyze the power spectral density of different modes of motion in frequency domain and compare them to experimental data. If we take a close look at the system response, we can recognize two peaks for each mode, right? The one with lower frequency and one with higher frequency. The lower frequency one corresponds to the natural frequency of the platform, and the higher frequencies for the wave excitement. But again, the general, the overall agreement is reasonable compared to the experimental data. Okay, the third part is about fluid-induced valve motion in a positive displacement piston pump. For this study, we employ FSI modeling together with compressible liquid to simulate the system. All right. I'm going to start with an animation. From CONVERGE Studio. This animation describes the case. In CONVERGE Studio, once the case setup is complete, you can create an animation of the moving geometry, right? This is done before you even start the CFD simulation. And it allows you to check how the geometry is moving and to make sure the motion is consistent with your real problem. In Converge, moving geometry cases are really easy to set up. And the piston pump case, for example, here is a multi-physics simulation. We use different physical models to simulate the problem. The flow field is turbulent, which is modeled by RNGK epsilon. Flow is induced by some oscillatory plunger in the piston, and the plunger itself has some time variable stroke profile. And the working cycle consists of suction and discharge. Bottom dead center is where the discharge cycle starts, and suction starts at the top dead center. And the compressible working fluid is, is described by equation of a state, where we can see density is a function of pressure. And the system properties listed here in this table, for example, the fluid is water. We know the stroke frequency, which is 270 RPM. The suction and discharge pressures are known. The spring preload is known. We know the spring constant, so we can apply the pre-deformation of the spring based on those two values based on Hooke law. And the minimum and maximum valve displacements are also known, and the system characteristics are listed here. All right, so as I mentioned, piston pump is a positive displacement pump. The pump is separated from the suction and discharge lines by some plate valves, and the valves are actuated by some fluid forces. And we don't have any active control system. We have some animation on the right shows how the suction valve move back and forth based on the balance of forces on the valve. This is done by two-way FSI coupling. And here we show that on the verge of opening, fluid forces and suction pressure should be balanced by the spring pre and post loads. And here we compare the suction valve lift with test data, right? So in the plot, you can see both opening and closing of the valve is matching the data. So it confirms that not only the displaced volume has been captured correctly, the compressibility effects are also captured by a CFD solver. The animation on the right shows contour of pressure over two physical cycles. Also, we can see clearly how AMR dynamically increases the grid refinement wherever and whenever needed. The total cell count is around 2.5 million for this simulation, and the computational cost is around 2,400 core hours for 2 cycles. The last section of today's webinar is about the erosion modeling. We'll discuss how it can be used with other physical models in Converge for multi-physics simulations. Let me briefly describe the erosion model in Converge first. So solid parcels and erosion modeling can be used to capture the erosive effect of a solid particle that impinges on a surface, right? So with this model, the surface geometry in the CFD simulation doesn't change. It remains unchanged, and we do not update the surface representation. Erosion is computed by some empirical correlation for the erosion rate. That's the ratio of eroded mass to impinged mass. We show the validation results on the top right, and we see on the bottom, we see the advection of the solid parcels by the flow, and we show contours of erosion ratio, eroded mass, and impinged mass over the wall surface. All right, so in Converge, a parcel represents a collection of solid, liquid, or even gas particles, right? Solid parcel modeling includes parcel-parcel interaction that can be combined with radiation modeling and erosion modeling. On the right, we show the erosion modeling panel in Converge Studio, where we have different erosion models available. And at the bottom, you see the liquid and solid parcels in a tank. Here we show a polycrystalline diamond compact drill bit case setup in Converge. This is again a multi-physics simulation with complex moving geometry. Heat diffusion through cutters and bit wall can be accounted for by conjugate heat transfer setup. Generally, cutting process normally creates some solid parcels, and impact of those pieces onto the bead wall causes some erosion in long run, right? And here we want to make those type of predictions. We have the details of the case setup, and we show some screenshots of the geometry from different angles. The fluid is modeled by Herschel-Buckley non-Newtonian model, and the drill bit rotates with 50 RPM, and we impose mass flow rate at the inlet and constant pressure at the exit of the domain. So when the erosion model is enabled, it can be combined with CHD and solid parcels to make some predictions. First, the mass that impinges on the bead wall can be predicted. The temperature of the bead wall itself can also be predicted. In the animation on the right, we see the motion of the drill bit. The wall is colored by temperature, right? The temperature increase shows some frictional heat flux, and that is included in the simulation as source term in energy equation. We also see the solid parcels, which are carried away by the flow. It is also possible to calculate the eroded mass. The animation shows the drill bit body. This time it is colored by the eroded mass, right? The red spots that you see, they are areas with higher eroded mass. And again, this eroded mass is caused by those cutting pieces. And on the plot, we see the evolution of the eroded mass over time that, it increases. And the next case that we are going to talk about is erosion inside a return pipe band, pipe band in a test loop of 32 meter. So we can see that we study the effect of the impingement velocity on the erosion rate. So for that, we double up the air mass flow rate, and we'll see how it affects the erosion rate inside the pipe and also the bend in the pipeline, right? The particle size for the generalized ERC, which is again some empirical model, is 300 micron. So we focus on the erosion of the first bend. We show on the top right corner plot. That bend is our focus for this study. And according to the empirical correlations, the erosion rate normally depends on the impingement velocity. If if we take a close look at the velocity contour over the band and also the particle concentration, we do see that the concentration, we have higher concentration over the outer radius of the band. So as a result, we can expect high erosion rate in that region. And if we take a look at the erosion rates contour, it confirms that the maximum erosion occurs at the first band and along the outer wall. And qualitative comparison to the test data confirms that the location of maximum erosion is right. And it can be seen that with doubling mass flow rate, the erosion rate scales almost linearly. With that, it was the end of this presentation. I'll pass it to my colleague, Mattia.